Hello everybody. We are going to discuss Chapter 10, which involves energy. So we're going to talk about how to calculate different types of energy associated with the reaction. And then at the end we're going to look about how we use energy in our daily lives. So we are going to cover sections 1 through 4. So section 1 discusses the nature of energy. So just kind of giving some background. Energy is the ability to do work or produce heat. And there are two main kinds of energy. First kind is potential energy. So this is energy due to position or composition. So when we talk in physics, we're talking more about position, like a skier being at the top of a hill. Or chemistry, we're talking more about composition. So the energy stored within the bonds between atoms in a molecule. The second type of energy is kinetic energy. This is energy due to motion. And so we'll talk about how this relates to temperature and heat. And so the equation for kinetic energy is 1/2 mass times the velocity squared. Okay, well, just like mass is conserved, energy is also conserved. So the law of conservation of energy says that energy can be converted to one form or another, but it can't be created or destroyed. So when you eat breakfast in the morning, you're taking in chemical energy. It's being converted to thermal energy to heat your body, kinetic energy so you can write or, go to gym class, things like that. So the total amount of energy is always going to be the same. It just changes forms. Well, we said that energy involves work. So work is the force acting over a distance. And this is used when we are converting energy. Some energy is also converted to heat through friction. And how much energy is converted to either work or heat depends on the pathway. The total is always going to be the same, but the amount that goes to either work or heat is going to be different depending on the path or depending on what happens. Well, things that are independent of the pathway are called state functions. So for example, if we look at the distance that an object travels versus its change in elevation. So let's say that you're going up a hill, you're hiking a 14er. Well, you have to hike a lot of switchbacks in order to get to the top of the hill. Well, your distance is going to be a lot more than if you just took a more direct route up the hill. But your change in elevation is going to be the same no matter which pathway you take. So a change in elevation is a state function, whereas distance is not. And let's look at heat and work versus an energy change. Well, we know that the change in energy, because energy is conserved, is going to be a state function. It won't matter on the pathway. But the amount of energy that goes to either heat or work is going to matter based on the path. So heat and work are not state functions. Alright, let's look at section 2, which discusses temperature and heat. Okay, because there is a difference between temperature and heat. Temperature is a measure of the random motions of the components of a substance. It's how quickly are the particles moving around. Warm water molecules are going to move around a lot more rapidly than cold water molecules because their temperature is higher. Okay, so you're measuring how quickly the particles are moving. So if we look at a container of hot water and cold water and we put them together, the energy is going to be transferred from the hot to the cold. And so if we're talking about temperature, the hot water molecules are going to slow down and the cold water molecules are going to speed up until we get an equilibrium. So until they all are moving at the same temperature. All are moving at the same speed, which would be our temperature. Alright, heat, then, is the flow of energy due to temperature difference. So when we had that container of hot and cold water, and we put them together, energy flowed from hot to cold. That's heat. The motion of the particles is temperature. So these two water samples would eventually come to the same temperature because of that flow of energy. So the energy lost by the hot water is going to equal the energy gained by the cold because we know energy is conserved. And the other thing we would have to keep in mind is that the mass of both water samples would need to be equal. If it wasn't, then, we wouldn't have an equal transfer. Okay, so temperature we said was measure of motion. Heat is flow of energy. So thermal energy is the random motion of all the components. So it's another type of energy. We talked about kinetic, potential. This is thermal. A flow of energy, which is called heat, is the way in which thermal energy is transferred from hot to cold. Remember, heat is flow of energy, in this case, thermal energy. All right, let's discuss exothermic and endothermic processes, because we've got two different ways that heat can flow. First thing we need to do is discuss the different parts of what we call the universe, or our overall experiment, if you will. Okay, the first part is the system. That's the part that we're interested in. If we're talking chemistry, these are reactants and products of a reaction. The surroundings is everything else. It's the beaker, it's the countertop, it's the air in the room, it's your hand, it's whatever isn't the reaction, basically. Okay, there are two ways directions that energy can flow. First is exothermic. This results in the evolution of heat, or the giving off of heat. So burning, you can feel heat being given off to the surroundings. So this means that energy is gained by the surroundings and it is lost by the system. So if we're referring to the system, if that's what we're interested in, this would be negative. Endothermic is the other type of energy change. This results in the absorption of heat, or the taking in of heat. Boiling is an example of this. Even though when something boils, we think of it as giving off heat, in order to get something to boil, we have to give it heat. You have to turn the stove on. So another example would be the potential energy that's stored in chemical bonds is converted to thermal energy via heat. So we have to give it heat in order to produce those bonds, make those bonds. All right, the last section we're going to talk about is thermodynamics. So this kind of takes all the stuff we talked about, puts it together. Okay, well, the first law of thermodynamics, which thermodynamics is the study of energy, says that the energy of the universe is constant. Okay, so even though we've got all these changes going on, the overall is the same. So the internal energy, or E, is the sum of the kinetic and potential energy of all the particles in our system, in what we're interested in. So this would be the flow of work, or the flow of heat, or both. Because remember, we said that work and heat were the two parts of energy. And so we can write an equation for this. We can say that the change in energy is equal to heat, which is Q, plus W, which represents work. And then based on whether or not heat is given to the system or taken from the system, makes these parts positive or negative. So let's look at that a little bit more. Well, there's two parts to a thermodynamic quantity. There's the number, which is the magnitude of the change. So whether, it's 10 or 20, it's an amount. Okay? And then there is the sign. If something is endothermic, that means that the energy of the system is increasing. Energy is being given to the system. This is positive. If it's exothermic, that means that energy is being given off from the system, or the energy of the system is decreasing. This is negative. Okay, so for work, it's positive if the surroundings do work on the system. If the system doesn't really have to do anything, if energy flows into the system, that's positive. The opposite would be negative, if the system has to do work, or if energy flows out of the system. So anytime things are going out of the system, it's negative. Anytime things are going into the system, that's positive. Okay, so practice these concepts with these problems, and we will discuss it more in class.